Welcome to This Explainer. Today, we're going to definitively untangle two of the most commonly mixed up concepts in all of math, factors and multiples. If you've ever caught yourself pausing, trying to remember which one is the divisor and which one is the times table, you are definitely not alone. But stick with me, because by the end of our time together today, you're going to have a rock-solid understanding of both. Here is our quick roadmap for today. We'll cover what factors are, what multiples are, put them head-to-head in a showdown, work through some actual practice examples, and finally, look at finding common ground between them. Okay, if you remember absolutely nothing else from this explainer, I want you to keep this one golden rule in mind. Factors fit perfectly into a number. Multiples are built out of a number. If you just hold on to that single sentence, you'll immediately grasp the complete opposite nature of these two mathematical ideas. Let's dive straight into section 1. What are factors? Also known as the dividers. So, what actually is a factor? Well, it's essentially a divisor. It's a whole number that chops up your target number perfectly, leaving absolutely nothing left over. For instance, the number 3 is a factor of 12. Why? Because 12 divided by 3 is exactly 4, with 0 remainder. On the flip side, 5 is definitely not a factor of 12, because if you try to divide 12 by 5, you get 2, sure, but you also have a pesky remainder of 2 left over. When you're trying to hunt down factors, it's honestly easiest to look for them in pairs that multiply together. Think of the number 12. We can arrange 12 items into neat, confined rectangles. We can have 1 row of 12, 2 rows of 6, or 3 rows of 4. By collecting both numbers from each of these multiplying pairs, we get our complete, perfect list of factors for 12. 1, 2, 3, 4, 6, and 12. Now, the absolute biggest takeaway here is that factors have strict boundaries. Remember our golden rule. Factors fit into a number. Because they have to physically fit inside, they are always going to be less than or equal to your starting number. This means your list of factors will always come to a firm end. Plus, here are 2 freebies you should just memorize. 1 is a factor of every number, and every number is a factor of itself. All right, section 2, what are multiples? The multipliers. Let's completely flip the script now. Simply put, multiples are just the results you get when you multiply a starting number. It's literally exactly like reciting the numbers in that specific number's times table. If you want the multiples of a number, you just multiply it by 1, then by 2, then by 3, and so on. It's really that simple. Unlike those tightly confined factor boxes we just talked about, multiples take a totally endless journey. Imagine the multiples of 4 just leaping forward along a number line. 4, 8, 12, 16, 20, 24. They land at perfectly equal jumps, marching forward forever and ever. Because multiples are built out of your starting number, they are always greater than or equal to it. And because numbers go on forever, their list is completely infinite. There is literally no such thing as a largest multiple. Also, if you ever need to check if a random number is a multiple of another, just divide it. If there's 0 remainder, congratulations, you found a multiple. And just like with factors, every number is a multiple of itself. Moving on to section 3, factors versus multiples. The showdown. Let's put these two side by side so you never ever mix them up again. They are exact opposites. To get factors, you divide exactly. To get multiples, you multiply outward. Factors are smaller or equal to the number, creating a limited, finite list that starts at 1 and maxes out at the number itself. Multiples, on the other hand, are larger or equal, creating an endless list that begins with the number itself and stretches all the way to infinity. Section 4, Worked Practice Examples. Let's put all this theory into practice. Okay, let's find all the factors of 24. We don't want to just guess wildly here. We want a methodical approach. We first identify all the multiplying pairs that perfectly fit into 24. We start systematically. 1 times 24, then 2 times 12, 3 times 8, and finally 4 times 6. Once we have our pairs, we just unpack them and neatly write them out in numerical order. 1, 2, 3, 4, 6, 8, 12, and 24. And there we have it, a perfectly closed limited list. Now, let's try multiples and watch how this builds outward. If we are asked for, say, the first 5 multiples of 7, we simply recite the 7 times table for the first 5 steps. We multiply 7 by 1, 2, 3, 4, and 5. Writing those results out gives us 7, 14, 21, 28, and 35. It really is that straightforward. Finally, Section 5, Finding Common Ground, finding the HCF and LCM. So what happens when we need to find the common factors of two totally different numbers, say 12 and 18? The process is incredibly simple. First, generate the limited factor list for the first number, 12. Then, do the exact same thing for the second number, 18. Once you have both finite lists right in front of you, you just scan them like a detective to spot the exact numbers they both share. When we compare those two finite lists we just made, the overlaps jump right out at us. The numbers 1, 2, 3, and 6 appear in both factor lists. Now, because 6 is the absolute largest number in that shared group, it earns the special title of the highest common factor, or HCF for short. This is a massively useful tool in math, especially when you're trying to simplify fractions. For common multiples, we basically do the exact same comparative process, but with our infinite lists. We send 3 and 4 out on their endless leaps along the number line. We write out the 3 times table, and right below it, the 4 times table. Then, we look for the specific locations on the number line where both of those numbers eventually land. By scanning those expanding lists, boom, we hit our first shared targets. We see both 3 and 4 land on 12, and a bit later, they both land on 24. Because 12 is the very first match we hit, it becomes our perfectly matched lowest common multiple, or LCM. Remember, since the lists go on forever, we literally can't find a highest common multiple, but finding the lowest one is incredibly helpful for things like adding fractions with different denominators. Well, we have covered a ton of ground today, clearly separating the dividers from the multipliers. But remember how we noted earlier that numbers can belong to many lists? I want to leave you with one final, kind of provocative thought. What is the single number that acts as both a fitting factor and a building multiple of the number 12? Think back to the rules we established for where factors end and multiples begin. If you guessed 12 itself, you are absolutely right. Keep that fun fact in mind the next time you're untangling these concepts. Thanks so much for learning with me today.